In the last section, we studied aromatic electrophilic substitution reaction, where a hydrogen on a benzene ring is replaced by a substituent. This can be halogenation, nitration, sulfonation, hydroxylation, alkylation, acylation. What if benzene already have a substituent? How does this existing substituent affect the next substitution reaction? This is the topic we are going to study in this section. Basically, there are two effects the existing group have on the next substitution reaction. One is reactivity. Some existing group make the next substitution reaction go faster, and some will make the next reaction go slower, and will classify them as activators, deactivators. Second is the orientation. The existing group controls the position on the ring to be substituted on the next reaction, and will classify them as ortho-para director or meta-director. This is an important table, and you must try to memorize it in order to do well in this section. Let's look at this table. Okay, towards the right side are called ortho-para director. So if benzene ring already contains one of these groups, then the next step, substitution reaction, will mainly take place on this ortho position or the para position. That's why they are called ortho-para directors. Now, you may notice that many of them contains lone pair electrons. Okay, particularly nitrogen, oxygen, single bond lone pair electron. And if a molecule contains lone pair electron, this lone pair electron can donate to the benzene ring, make electron rich, and the more electron rich benzene ring will reaction faster on the next step. Okay, next the substitution reaction become faster, and that's why ortho-para directors are also activators, because they make the next reaction go faster. All right, and so all these groups, so nitrogen lone pair electron, oxygen lone pair electron, methoxy, amines, make reaction go faster, also ortho-para director. Okay, note that the benzene ring itself is also an activator, ortho-para director. So if benzene adds to another benzene, and that make it ortho-para position reactions. Another one to remember is alkyl groups. Alkyl groups are also ortho-para director activator, because they donate electron to the benzene ring, so make reaction go faster. Now towards the left side, they are meta directors. So if benzene already have one of these groups, then the next reaction mainly take place on the meta position. Okay, mainly on the meta position. That's why they are meta director. And note that they contain CO double bond, and CN triple bond, and NO2. And you may remember that these are electron withdrawing groups. They take electron away from benzene ring and make electron less rich. And so the next step must become slower, and therefore they are also deactivators. So most meta directors are deactivators. Now, one exception, these are halogen atoms. Halogen atom has lone pair electron, so the lone pair electron can donate to the benzene ring. On the other hand, they are also negative. Okay, they have high electronegativity, and that make them deactivators. Okay, so halogen atoms are deactivators, but also they belongs to ortho-para director. Okay, so this is an exception, because most ortho-para directors, they are activators. Only halogen atoms, they belongs to ortho-para director, but they also belong to deactivators. So remember that. Now on this table, the more towards the right side, the stronger the activators are. So alkyl groups, they are stronger activated than benzene ring, but the methoxy, hydroxy are even stronger. Amines are most strong activator. Okay. On the other hand, if amine is protonated, becomes positive nitrogen, then they become the strongest deactivator. Okay, on the far left, yes, so positive nitrogen, a strong deactivator, and then NO2, nitro group, and then CNO, nitrate, okay, and then CN, triple bond, and then CO double bonds, okay. So this, again, is a very important table. I want you to spend time on it, and this is the key in this section. Here shows an example. Okay. At this point, you should be very familiar with the aromatic electrophilic substitution reactions. So when you see nitric acid combined with sulfuric acid, you know it's a nitration reaction. Sulfuric acid is a catalyst, and the net effect is to replace one of the hydrogen by NO2. And so NO2 replace one of the hydrogen. That's a nitration reaction. But where does it go? Okay, and last slide we show that this depends on the existing substituents Y. So here experimental shows that if the substituents are these groups, and that's an N positive charge, NO2, CO double bond, CN triple bond. From last slide, we know that these are strong electron withdrawing groups. They belong to deactivator and meta director. So experimental show that meta position, they have 87% product, 91%, so majority are meta product, substitution product, and only 2% author, 11%, 7-2, so small amount author pair, and majority is meta position. Okay, that's is consistent with we learned in the last slide. Now, if Y is CH3, which is alkyl group, hydroxy group, okay, nitrogen, and with lone pair electron, okay, then from last slide we learned that they are activators and they also para director, and so experimental show also 63% para, 34%. Only 3 meta position. Hydroxy 50-50 on ortho para, only 0 on meta position. Okay, and again consistent with the table. Halogen atoms, we learned that they are deactivators, but they also are ortho para director. And experimental show 13% ortho, 86 para, 1% meta position. Again consistent with the table. Practice. Predict the major product of sulfonation of toluene. Now you should remember from last section that sulfonation means you combine SO3, sulfuric acid, and the sulfuric acid is as a catalyst which will protonate SO3 becomes SO3H plus. Okay, and then benzene attack, elimination. So the net effect is a hydrogen on the ring is replaced by SO3H. Okay, that's called the sulfonation reaction. But where does it go? Okay, from the last table, we learned that this depends on the existing group, and here is a meta group. Meta is an alkyl group. Alkyl group is a activator and also ortho para director, and therefore the product must be ortho and para. In the next few slides, we're going to explain the origins of substituent effects. Basically, there are 2 factors: inductive effects, resonance effects. Inductive effects is the withdrawal or donation of electrons through a sigma bond or single bond. Resonance effect is withdrawal or donation electrons through a pi bond. When benzene is attached to a heteroatom, whether it's chlorine, oxygen, nitrogen, or even carbon that is connected to oxygen, nitrogen, these heteroatoms take electron away from benzene ring through the sigma bond or single bond. And this is called inductive effect. So based on this inductive effect, almost all substituents are electron withdrawing group. So they should deactivate the benzene ring. A pure group is electron donating, so it's through inductive effect, it actually activates the benzene ring. There must be other factors that oppose this inductive effect. Otherwise, hydroxy should be a deactivator. But from last table, we know it's a very strong activator. When benzene ring is attached to a CO double bond, the pi electrons on benzene ring may move through alternate double bond, single bond, double bond to oxygen atom. Another way to say this is that we can draw resonance structure to show the pi electrons on benzene ring may move to the electronegative oxygen, make oxygen negative, make benzene ring positive, and therefore CO double bond is a deactivator. Okay, I suggest you to draw these resonance structures as many as possible, and you can find the forms in the textbook. And these resonance forms suggest that it is the ortho and the parallel carbons that have positive charge. So although the whole benzene ring is deactivated, the most affected carbons are ortho-parallel carbons. If the benzene ring still reacts, then the most likely to react carbon is the metal position. Okay, so the metal positions, because they are less affected by resonance structure. And therefore, CO double bond is a deactivator, it's also metal directing. Okay, now we can draw similar structures for CN triple bond, for NO2. Okay, all of them shows that they deactivate the benzene ring, but the most deactivate is ortho-parallel. So if they react, they will react on the metal position. So they are metal directing. Okay. Now, from last slide, we show the inductive effect, and this slide resonance effect. Both effects shows that CO double bond, CN triple bond, and O2, they are deactivators, and they are metal directing. When benzene is attached to hydroxy group, the lone pair electron can move through this single bond, double bond to benzene ring. Or we can say through resonance structure, the lone pair electron goes to the benzene ring to make benzene ring electron rich. And therefore, hydroxy is an activator due to the resonance structure. Okay, now I again suggest you to draw the resonance structures, and you will see the resonance structures indicates the ortho-parallel positions are the most affected. Okay, they are most electron rich now. All right, so the benzene is activated, but it's the ortho-parallel that is the most activated, and therefore it is ortho-parallel directing. Okay, activator and ortho-parallel directing. Now we can draw the similar structure for amine, for even chlorine. They all donate electron to the benzene ring, all right, to activate the benzene ring. On the other hand, we also saw in inductive effect that take electron away. Chlorine, oxygen, nitrogen, they are all electron negative. They take electron away due to the inductive effect. So inductive effect, resonance effect, they contradict each other. It turns out that for oxygen, for nitrogen, resonance effect outweighs inductive effect. In fact, in most cases, resonance effect is more important. And therefore, for hydroxy, methoxy, amines, they donate electron due to the resonance effect to make benzene more rich in electrons, and so activate the benzene ring, particularly on the ortho-parallel positions. Okay. On the other hand, halogens in halogen atoms, the inductive effect outweighs resonance form. So due to the inductive effect, benzene ring becomes deactivated. But the chlorine still donates electron due to the resonance to make ortho-para electron richer than the metal position. So even though the whole molecule is deactivated, if they react, it's the ortho-para positions because they have more electrons, electron density than the metal position. Okay, all right. So this slide shows that oxygen, nitrogen, chlorine, they all have lone pair electron. Resonance form make them ortho-para director. And for hydroxy, amines, methoxys, resonance form is more important, so they are activators. For chlorine, bromine, inductive effects outweigh the resonance form, so it's a deactivator. Let's go back to this table. So atoms with lone pair electrons, such as nitrogen, oxygen, hydroxy, methoxy, amines, they donate electron to the benzene ring through resonance effect, and although they also withdraw electron due to electron negativity, resonance effect is more important, and therefore the benzene ring is activated. So these groups are activators, and the most activated position are ortho-para. So they are ortho-para director, and they are activators. And this also includes the benzene ring alkyl group. So the more to the right side, the stronger the activator. The groups contain CO double bond and the CN triple bond, NO2. So these groups, they withdraw electron from benzene ring both through inductive effect and the resonance structure, and therefore they are strong deactivators. And they deactivate mostly on the ortho-para position by resonance effect. So ortho-para is the most deactivated. So if react, they react on the metal position. They are deactivator and also metal director. Halogen atoms are very special. They have lone pair electron that donate through the resonance effect. They also are electron negative, so they take electron away. Inductive effect is more important in this case, and so they are deactivators. But the lone pair electron goes to the ortho-para, make ortho-para electron density more than metal, so they are ortho-para directors. Let's look at this bromination reaction. Okay, when you see bromine molecule with the catalyst iron bromide, you know it will replace one hydrogen by bromine. Okay, that's bromination reaction. But where does the bromine go? Okay, so we look at the two substituents in this molecule. You already have a methyl group, which is a ortho-para director. In this molecule, ortho is here for the methyl, so this is ortho position. And the para already have a nitro group, so it cannot go. And on the other hand, nitro is a metal director. For nitro, metal is also the same location. It's a metal for nitro. So both substituents tells us the next one should go to the same location. Okay, so if directing effect of the two groups are the same, results is additive, and therefore we predict the product should be here. The bromine should go to here. Now, if you go to here, that gives you the same product. Here is a nitration reaction. Okay, when we combine nitric acid with concentrated sulfuric acid, we know one hydrogen on benzene should be replaced by NO2. But where does NO2 go on the ring? Well, this ring has two groups. One is hydroxy, one is methyl. Both groups are ortho and para director. For hydroxy, ortho should go to these two carbon. For methyl group, it should go to these two. And therefore, these two groups contradict each other. So it says that if the directing effect of two groups oppose each other, the more powerful activating group decide the principal outcome. In this case, hydroxy is more powerful than methyl. Now, if you don't remember this, go to the table, you will see hydroxy is to the right side than the methyl or alkyl group. So it's more powerful. And therefore, the product should be determined by hydroxy. And therefore, it should go to these two positions. All right. So the product is predicted to be here. In this molecule, we have two substituents that in the metal position. Both are ortho-para director. Although chlorine is a deactivator, it's also an ortho-para director. So for methyl, it predicts to be here, A, ortho, and here, B, that's a metal para position, and this is another ortho. So let's say this is C. For chlorine, it's also ortho-para. So again, you predict B, that's a ortho, and C, another ortho, and A, it's a para. So they have the same directing places. However, because chlorine and methyl are close to each other, the carbon C is very crowded, and so the reaction to this carbon is very difficult, and the product mainly on the A and the B. So this is on B, and this is on A, and this is not formed due to the two substituents so crowded to each other. Okay, so how do you make a molecule that three substituents are close to each other? You don't want to start a reactants that has two substituents on the metal position, because that makes the center carbon too crowded. Instead, you can start with two adjacent substituents, and then you can add here to make a three substituted compound. Practice. What product would you expect from bromination of para-methyl-benzoic acid? So this is the para-methyl-benzoic acid, and bromination reaction means you add bromine with the catalyst iron bromide, and that will replace hydrogen by bromine. But where does it go? So we look at two substituents. Methyl is ortho-para director, so should go to these two positions. And benzoic acid, carboxylic acid, has a CO double bond with OH. That's carboxylic acid group, and that's a electron withdrawing group. It's a deactivator and a metal position. So for this one, metal is also the same location. So two substituents has the same directing effect, and therefore they add together. Bromine should go to either this place or this place, and the product is here. Practice. How do you synthesize this compound from benzene? So compare reactants and the product, we see that we need to add two substituents. One is bromine, one is acetyl group. Bromine can be added by bromination reaction, and acetyl group can be added by Friedkraft's acylation reaction. All right, so there's two possible ways. One is you do bromination first, and then you do Friedkraft acylation reaction. Okay, the other way is you perform this first, acylation reaction first, and then bromination reaction. Which one is better? Which one works? Which one doesn't? Okay, we'll see each in detail. Let's do the bromination reaction first, and then we perform Friedkraft acylation reaction. So after bromination reaction, one bromine is added to the benzene ring. Now remember, bromine is ortho-para director. So the next step, it will go to the ortho-para position. All right. So Friedkraft acylation should give you this product. There may be some here also. Okay, but definitely not a metal position. But the desired product is the metal position. And therefore, if we do the a bromination reaction first, we cannot get the desired product. We get the product that is not what we want, and therefore this method doesn't work. If we perform Friedcraft acylation reaction first, the product is an acetyl group on the benzene ring, and the acetyl group is a metal director, and metal is here. So then we do bromination reaction that will give you the desired product. So this example shows you that when you add two substituents to the benzene ring, you need to think about which method, the sequence, all right, that will give you the desired product. Here's another example. How can we synthesize this compound from benzene? Again, we can perform nitration first, and then Friedcraft acylation to add the acetyl group, or Friedcraft acylation first and then nitration. Which one works, which one doesn't? Can we perform nitration first and then Friedcraft acylation reaction? Nitration gives you a nitrate group on the benzene ring, and the nitrate is a metal director. So the next step should go to here, which is exactly what we want. And so you would expect this works. However, the next step is the Friedcraft acylation reaction. And there are limitations on Friedcraft acylation reaction. One of the limitations is that the benzene ring cannot have strong electron withdrawing group. Nitro is a very strong electron withdrawing group. And therefore, the Friedcraft reaction fails because the benzene contains a very strong electron withdrawing group. It cannot perform Friedcraft reaction on the next step. So this doesn't work. If we perform Friedcraft acylation reaction, the product is adding an acetyl group to the benzene ring. And the acetyl group is a metal director. So the next step goes to here, metal position. And the product can be easily achieved by adding nitric acid and sulfuric acid mixture. So this example shows that when a reaction involves Friedcraft acylation reaction, not only the sequence you need to consider, but also the limitations of the Friedcraft acylation reactions needs to be considered. Homework. Please work on problems 16.8 to 16.12, and then 16.14, 16.15. Also work on some additional problems in the textbook.